Okay, greetings and salutations, scientists. So we're going to talk about drawing covalent bonds, and I'll give you a few examples for you to review and study and use as a guide to practice with. So starting with fluorine. So let's say, for example, you're given a question that is draw the Lewis dot structure of a fluorine compound. And that's it. So you know that fluorine is your only element. And we'll start with figuring out how many valence electrons does fluorine have. And looking at my periodic table to see what group it's in, we see that fluorine has 7 valence electrons. 7 valence electrons are a lot. It is almost filling up its outer shell of 8, meeting the octet rule. Octet meaning 8, because oct like octagon. However, almost is not 8. Almost 8 is not 8. We have 7. So it needs another electron to fill up its outer shell. Next, we want to determine what kind of element is it, or what kind of bond would it create. So fluorine is non-metallic. And since we're given that only fluorine is in this compound, we know that only non-metallic atoms are in this compound. And if we have non-metallic atom filling or bonding with a non-metallic atom, so 2 non-metallic atoms, or a bond between 2 non-metallic atom types, that makes it a covalent bond. If one of them were metallic, then it would be an ionic bond, which is another video. So we have a covalent bond, and our covalent bonds mean that we're sharing electrons. Ionic bonds will give electrons away. Covalent bonds will share an electron. So if we have fluorine only, and it needs to share electrons with another fluorine, how many does it need to share to gain enough electrons to meet the octet rule? Well, since it has 7 electrons, or 7 valent electrons, it needs one more electron to fill that outer shell and to satisfy that octet rule and have a total of 8 valent electrons. So let's start with the simplest solution, which is just adding one more fluorine. So if we have a single fluorine with 7 and another fluorine with 7, then you'll notice that I'm drawing that the single or lone electron pair or electrons are between the 2 atoms. That's intentional. All right. The standard nomenclature is not to draw the single one out here or up or bottom or anywhere else. It's always in between the 2. And that just will simplify when we're drawing the symbol to share, or how to signify that they're sharing an electron or electrons. It will let us know that simply that which ones are being shared and which ones are not being shared. So we have our 2 fluorine electrons, and we need to see if this will satisfy the octet rule. In other words, if they're sharing, and this is just a single line between the two, free electrons, if they're sharing a single electron apiece, well, we have 8 total electrons for each element. So counting them up, we have our 1, 2, 3, 4, 5, 6, 7, and because it's sharing this one over here, that's our 8. And looking at our other element, the other fluorine, 1, 2, 3, 4, 5, 6, 7, and sure enough, because it's sharing this one, another 8. So they both have 8 electrons now because they're sharing that one electron. So this is a happy compound. Every atom within it has a full octet valence shell. Each atom has 8 electrons. Everybody's happy, and this is a good stable bond. And again, because they're both nonmetals, then it is a covalent bond. And obviously, if one were not a nonmetal, or if one were a metal, because it's the same element, both would be metals, which would be a metallic bond, which we haven't covered yet, and that'll be in a later video. So in this case, it's a single atom, which means that it has to be a covalent bond. It can't be an ionic bond if it's a single atom, because an ionic bond requires a metal and a nonmetal. So that's kind of the simplest version. This would be written as, so this would be your final solution if you wanted to write it as a compound equation. It would just be F2, which means 2 fluorine atoms. Let's look at a slightly more complicated example. So instead of just a compound with 2 of the same elements, instead, let's look at one with 2 different elements. So if I were to give you hydrogen and phosphorus. So looking at my periodic table, both of them are nonmetals. And since they're both nonmetals, I have a non-metal bond, which means it's a covalent bond. So already I'm off to a good start. I'm going to draw my symbol for each. And now I'm going to figure out how many valence electrons each has. So hydrogen just has a single valent electron. Phosphorus has 5. So 1, 2, 3, 4, 5. And again, I drew it in the Lewis dot structure form where I have filled out each of the 4 sides first and then added my second electrons until I've run out. So I've got a single valent electrons, or really just a single electron for hydrogen. So I just drew that one electron here. For phosphorus, I have 5, so filled up my 4 sides, and then drew the 5th one as a pair. And again, just like the previous example, I left a lone electron, or a free electron, between my 2 atoms. So if I want to do the octet rule, as always, octet rule, although it means 8, what we really want is just a full outer shell. Hydrogen, its only shell, that 1s shell, has a maximum of 2 electrons because it's 1s. So hydrogen can only have 2 electrons in its shell to be happy. Phosphorus, on the other hand, wants 8 valent electrons to be happy. So hydrogen needs 1 more. Phosphorus has 5, so phosphorus needs 3 more. Again, hydrogen wants a total of 2, phosphorus wants a total of 8, and so we're figuring out how many each one wants. So how can hydrogen and phosphorus share an electron so that they're both happy? Well, they're sharing these electrons, then we have 1, 2, and hydrogen has its 2, so hydrogen is happy. It's gotten its 1 more. And phosphorus has 1, 2, 3, 4, 5, 6, but it wants 8. So phosphorus is not happy. This is not a full compound. And again, I'm limited in that I only have phosphorus and hydrogen, and I can't use anything else to try and complete phosphorus's octet. So I have to add hydrogen atoms until phosphorus has its 8. The way I will do that, same as I did before, filling out each of the 4 sides of the single, and then any remaining, make them pairs for my phosphorus. I already know these 2 can share that electron, or their electrons, so that this hydrogen is happy. And then if I draw another hydrogen here, drawing their free electron between again. Now this hydrogen has 2, it is happy. And then finally, a third hydrogen, and this hydrogen has 2, so it's happy. And we just need to check phosphorus. So phosphorus has gained from its 1, 2, 3, 4, 5. It is sharing a 6th, a 7th, and an 8th electron. So phosphorus has its 8, and each hydrogen has 2. Everybody's happy. Everybody has a full outer shell, and we have our answer. So again, we are drawing our hydrogen atoms in line with our Lewis dot structure. So we wouldn't want to draw like a hydrogen atom out here and then drawing some weird diagonal there, or to have this electron going up here, right? We want everything to be in these straight lines so that it is just, oh man, I erased too much, but hopefully you get the idea, right? So everything should always be off to one side, imagining there's this box around each atom.